The objective today is to describe how protocols work in the TCP/IP architecture. So I apologize in advance, I'm about to complain quite a bit about all the jargon that goes into networking. I don't exactly know who's responsible for it, but it is driving me crazy. So I'm going to go into that first thing today, and afterwards I'll go ahead and start hitting up all those protocols that I mentioned we'll be doing in the objective. Your objective to be describing each of them, and all of the layers that contain protocols such as these are considered to be the TCP/IP architecture. So when I first started teaching computer science, I struggled with the semantics of everything. For instance, what is the difference between protocol and encoding? So just that took a little while. Some of the biggest words out there, like serialization. This word just means bytecode. So I don't know who these guys are, if they're like lawyers or something who decide to use this crazy jargon, these crazy words. I wish they'd just keep things a lot simpler. But that's where I come in. That's what I'm going to try to do for you today. And all this vocab frustration I had, and I'm sure you have it too if this is an introductory class for you. If you have any of those frustrations, just remember that attitude is everything. I had to remember that myself too. If you could answer that question I just asked, what's the difference between protocols and encoding, then maybe this video is going to be a bit too low level for you. I'm going to dig into semantics the entire time. But of course, feel free to stay. See if you could catch me making any mistakes, and then I'm very open to hearing about those. That way I could redo this thing and fix them. So here we go. If you're taking notes, protocol is a big communication thing. When you're hearing protocols, this is two people who have decided to agree on the meaning of something. And that makes sense. If we're communicating from long distances, we need to agree on how we'll be talking to each other. And then to get all philosophical on you, I guess that's true for what we're going to call decent society and when we use ones and zeros. I think in a country like America right now, we are struggling to agree on the protocols of what being decent to each other means. Do not fear, I will not get into those things, but I think we can agree that if you watch the news, you're going to be walking away from that thinking Americans lack basic protocols. But maybe some of them were encoded to behave the way they behave. And that's where this word encoding comes into play. Encoding is how the computer will interpret those ones and zeros. We've made the protocol that the ones and zeros will mean something, and now this is going to be encoded into the computer. And those ones and zeros are flowing through things on buses. You have a control bus, an address bus, a data bus. And the ones and zeros are being picked up by the CPU, memory, and input-output devices. And notice they are all connected together. So the ones and zeros are taking this bus, well, not that kind of bus, more like a bus like this. So the ones and zeros are going to be all over the place here. And because computers are designed the way they are, they're going to know how to use these encodings. And the amazing thing about being a programmer is you're able to change this without building a brand spanking new computer from the ground up. We have these embedded chain reactions that will occur so we can really manipulate the computer into doing whatever it is that we want. Okay, so let me try to simplify all this with some examples. When you go to example.com, you start by typing it, right? The letter E and then X and so on. Well, this is, I'm going to call this an ASCII action. I think I may have made that term up, but this is an encoding. This is something the computer knows. So you're putting these series of ones and zeros together into your browser, and then when you go ahead and push enter, this is when you take your first step into the TCP/IP architecture. Your browser is an application. You're at the application layer. And in this scenario of using a browser and going to a website, you are engaging with the HTTP protocol. Well, actually, hopefully you're engaging with HTTPS, but I have a whole nother video about that. For now, I just want to walk you through the layers using web browsing as my example in the protocols that are involved in web browsing. And if you'd like to see firsthand how this protocol is working, or at least the words associated with the protocol, I'll be showing that to you in just a little bit when I go to a website, but anybody can see this if you right-click on a website, click Inspect, click Network, and then you'll be able to click a tab. I'll show you this in a second, but the tab will show you the headers. And think about that word for a second. What's a head on a human being? What is somebody who is a head? A header is like the first in a series of ones and zeros. And a great way to imagine this, at least this is what I'm thinking, is all of the different protocols are like different color one and zeros. You know, they're not even colored, they're just bits of electricity. But for each protocol, I think of it just being a different thing. It's a different style, it's a different beast. And like somebody in my class the other day pointed out, this is all very repetitive stuff. I think you could get paid big bucks for tolerating repetitiveness. So let's look at the strict definition of protocol before we move any further. It is just rules and procedures for communication. So when multiple protocols work together, it's called a protocol suite or protocol stack. You're going to hear the TCP/IP stack. I've heard networking stack as well. And this is famous, though my biggest complaint is there's already something just like this with the same protocols being used as examples, but it's a whole nother model. It's called the OSI model, and I highly suggest you watch that video of mine before this one, because the OSI model I like for students because it's a little bit more detailed, or at least there's more steps to it. So if you can memorize those steps, moving down to, or I should say over to the TCP/IP architecture or TCP/IP model or TCP/IP stack or suite, see all these words meaning the same thing. Going from 7 layers to 4 is just going to be so much easier. I suggest start with the hard one first. So make sure you got your definitions down. What is a protocol? And now let me rant a little bit more. It's maddening the fact that this protocol suite is just named after 2 of the random protocols that's inside of it. And you don't even have to always have TCP. You could have UDP when you're browsing the web. Both are great protocols, good for different scenarios, but at least IP stays the same. There's really no other thing but IP. We do have IPv4 and IPv6. We're trying to move away from IPv4, that is only 32 bits long, and go over to this IPv6 internet protocol because it has 128 bits. That's quite a bit. So maybe the person who named this architecture or this suite TCP/IP did so because it thought these were the most important of all the protocols. But maybe if you take a networking test and you have to answer questions about this, you can remember my anger towards the TCP/IP architecture. Because just like this guy in the picture, I'm like, he is not a unicorn and TCP/IP is not a good name to describe an entire series of chain reactions that happen when people communicate on a network. Okay, that should be the end of my rants today, I promise. So to dig into all the words, what's nice about this TCP/IP view is you only have these 4 large categories right here, and if you're taking notes, I'd write them down. You have your application layer, your transport layer, your internet, and your link. Link layer is just a cool word to say. Try that 10 times fast. But notice over here, it says UDP, and that's what I was saying earlier. Like, this is the TCP model, and TCP is not even present in this particular example. So how are you going to name a model after... Okay, sorry, I said I would stop ranting, so let me stop that. Your next think right here is what are some protocols you recognize below and what layer are they associated with? So I'm looking here at the TCP/IP architecture and I come over here to the protocols and I totally know HTTP, so I write that down on my paper. Maybe you've never heard of POP3, but I'm hoping you've heard of DNS if you're in the class. If not, no worries. I've started this entire YouTube video series where I take all the vocab words that I deal with on a day-to-day basis and I make individual videos just on the word. At this point I have no idea what to call this series, but it should just be something helpful for you to be able to quickly click on and then just get a deep dive into that particular vocab word, seeing how, so many of them are on tests. And what I like to tell my students is at the very end of the day, if you haven't created too much in this world of networking or computer science, if you could just talk the talk first, you should be able to get your foot into the door and get help with the creating part later. So moving on, there's already this OSI one, so why are we going to study this TCP/IP architecture in class? Well, it's very common. I wonder if it's so common you already know what TCP/IP stands for. And to give you a little history here, this concept was first developed during the 1960s as part of the Department of Defense's Advanced Research Project Agency, ARPA. That might sound familiar. and it was developed in an effort to build a nationwide packet data network. It was first used in Unix-based computers and in universities and government installations. So calling it TCP/IP has been popular for a while. Remember, the Osi model is using the same protocols, so it's not like the idea of putting network protocols together to send information was created in just one place. And like my friend in networking likes to say, he doesn't know the model at all, but if he has a job to do, he knows how to get that job done. He knows how to program, he knows how to do socket programming. So I guess that means he'll be totally fine, like making something work, even if he doesn't know this academic terminology that I'm using here in class. But trust me, you guys, this is definitely worth learning because it's a good way to just see what's going on. And seeing how the internet's a pretty dang big place, these protocols are really big deals. And here's something interesting. I did go on a hunt to find the exact paper or maybe the official publication of the OSI standard. And I want to use this site as the example of what I said earlier, where I'm going to right click and look at the network and then look at the headers. But the depressing part of this is if I wanted to read more, they're going to charge me to do that. So let's just take a deeper look into their website and see what they're doing here. I'm going to click network. I'm going to refresh the page so I can see it load. If you're wondering why that took so long, though I edited out the part where I was waiting, but the reason these numbers are going to be really high right now is because I just got an Xbox for my children for Christmas and we're updating right now. So I know there's a lot of traffic on my network, but let's look at one of these. Actually, the first one here, and I'll click it, and there you go. This is our headers tab, and then if I click the next one, you'll see the details of this protocol working. It's using a get method, so it's trying to get information there. There's that shopping cart right there I told you about. So at least their site is secure. This is the International Standards Organization. Or I should say International Organization for Standardization. But we need to go ahead and make our next step down to the second layer. We've stayed up here for quite a long time. So before I do that though, quick question of these two. Now that you're learning quite a bit about this one, if you don't answer this now, please answer it by the end of the lesson. But I'm wondering which one you prefer, the OSI model or the TCP/IP model. And it's nice to be able to look at them next to each other like that. So here's our TCP header. Once you've used your ASCII encoding thing to go ahead and create ones and zeros requesting a web page, that gets handed off to HTTP, and then HTTP hands itself off to this TCP header. And again, this is called header because it's going to be at the head of some other bits, just like that HTTP was. But in this one, you're looking at information such as the port you're looking to connect on. If we're talking HTTP, that's going to be port 80. If this is the first packet, it'll go ahead and say it's the first packet. It'll have a number to make sure the correct server is acknowledging it, and you don't want some sort of breakdown, so this is all very sequential here. And here's some other information, but I don't want to spend too much time digging into the TCP header. I'm just thinking here's just the next set of bits that you're looking at. Maybe a prettier view of the TCP header. Do you remember the slide before where it said how many bits make up the port numbers? If you've watched previous lessons of mine, I've told you that ports can go up to 65,000 something. So here's that picture again for you real quick. 4 octets, that kind of looks like something I know I've heard of before, and maybe this picture will give you a hint. It is a book my daughter likes, by the way, but right here I'm saying all TCP traffic rides with IP packets. So whether it's UDP or TCP, at least you know IP will be with these protocols. And we're talking about series of ones and zeros that make very perfect sense when they're in an exact type of order. I mean, they at least make perfect sense to the computer that's interpreting them. And don't forget to have curiosity in here. I encourage that in all my classes. Is there an alternative to IP? I'm telling you there isn't, but maybe there is. Maybe the teacher could be wrong. I told you the alternative to TCP is UDP, so I researched a bit and I found nothing. So just want to throw that out there, a challenge to you. I mean, the objective is to describe how protocols work. TCP is optional, whereas IP does not seem to be so. Now, when you look at the IP header does not include information necessary to send traffic to a web server listening on a specific TCP port. But the cool thing about IP packets, or numbers, I should say, sorry about that. So the cool thing about IP headers, geez, those other words were completely wrong and I'm really messing up the words, being this is a lesson on words. So the IP header has this thing called a time to live. And that is a genius feature to me. You can use that little concept for quite a few things, including security. But another one I really like is for this trace route concept, you can literally from your command line measure how many hops your packet will make before it gets to its destination. So just the other day I was curious about a server in Canada. I'm here in Colorado. I use this trace route command and I went to Dallas before going up to Canada. And I'm like, why are my ones and zeros going to Dallas first? Well, it is the internet moving at almost light speed, so it really didn't take a noticeable difference to me. And I just found that interesting that that's the path that my packet went. And of course, in the IP header, you have some things that make sense, like the protocol number field specifies what type of traffic that the packet is. So whether it's an ICMP or a UDP or TCP, like all these things have their own unique numbers to them, which is a pretty cool thing to me. And here is a better visual rather than just listening to the words on that slide. Here's the visual. We have an IPv version. We got IPv4 and IPv6. And then the next set of bits will be about the length. And there's more and more bits about other things, but this is that funnest feature to me, or funnest set of bits. This right here will have that protocol, like this is an IP header that says I'm going along with a TCP right now. Transport a transmission control protocol. And then I'll have a source IP, destination IP within this header. And then a few options over here. So your think right share, what's the difference between the TCP header and the IP header? So okay, so far we've gone through the application layer, passing a request to the transport layer with these two combined, we call this a segment. After that, we tacked on an IP header, so now that leaves the very last one. So this is our last stop. It's the end of the line. Let's get off this crazy train. We're going to take a quick field trip before I give you your DOL here. So first I want to show you what this Ethernet frame concept is. In our OSI model, we learned about the data link layer having a MAC address, and that's something that switches use. When the TCP IP architecture, that layer and the physical layer are combined. So the physical layer being just the bits, this is the Ethernet protocol on the physical layer basically. So here's a preamble saying like I'm an Ethernet protocol. Some other options would be like a Wi-Fi protocol maybe, or a point-to-point communication protocol. So there is some variety down here even at the lowest of levels. Next you have what's called a start frame delimiter. This will signify that the destination MAC address field begins with the next byte. So this one's one of those funny ones. This is a big networking thing, right? Where somebody says like, okay, I'm going to speak. Okay, the next word I'm going to say is 5 bytes long. Okay, here's 2 bytes of what I was going to say, and then like so on. You just keep setting up the computer for information. That way everything is like nice and tidy, and you've made sure you've taken all the bits that was intended to be sent in the transmission. It's kind of like that commercial, Can You Hear Me Now? There's just like constant verification to the computer that it's getting all the data it's supposed to. And that's why at the very end of like all of this, you have what's called a frame check sequence. And this is a 32-bit cyclic redundancy check, which that's a fancy word, right? I'll have a video purely on that term, but it's existing so we could detect corruption in the data. And you may be used to hearing Ethernet not as a protocol, but as maybe a cable. It's not the name of the cable. Like this is a CAT cable, maybe Cat 5, Cat 6 or whatever. But this protocol it's using, or that we associate with these wires, is the Ethernet, the lowest of level protocols. Over here is a wireless standard, and then this was confusing me, the difference between standards and protocols. Basically, the consensus is many protocols are standards, but the word standard is a document that specifies something. that has overwhelming support. Okay, isn't that what a protocol is sounding like? Instead of just relying on Google, I used Bing to also search for this question. And I like the results that I found here. Somebody said not all protocols are standards. Not all standards are protocols. Over here, a protocol is not a set of rules. A protocol is the thing those rules describe the rules of. This is why programs implement a protocol and comply with a standard. Over here, blah, 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 but a standard is a formalized protocol accepted by most of the parties. So if this is a discussion on software engineering on Stack Exchange, I mean, we're not the only ones who struggle. At the end of the day, you create something that works or it doesn't, right? So that's the end of the lesson. Our very last check for understanding is, can you name the 4 layers of the TCP IP architecture? So application, transport, internet, and link. That's worth memorizing there. And then here's your DOL. I just want you to explain what happens when you make a request for a web page. I'm very curious to see if you can name all these protocols that we've gone over by memory. So good luck with that and don't give up.